Hello everyone, I am Ziat and I am going to talk to you about a work we have made with Matthieu, Dien and Vincent Botbol, which is about automated random testing with constraint type. So in this work we are interested in programming errors that we can detect automatically. So for example, such errors can be type errors. So suppose you have a strictly typed programming language, you will generally not be allowed to add integers with strings. So this will trigger a type error generally. So another kind of programming error can involve numerical constraints. So for example, suppose you have a type interval, which is a pair of integers. But not all such pairs are valid intervals. So here we have written in a commentary a relation that the type interval should satisfy. That is, the first member of the tuple should be smaller than the second one. So this would be a valid interval, but this would not be a valid interval. Moreover, if we have functions, we should ensure that the function do not break the invariant. So here we have a function that aims at computing the negation of an interval. But here it is buggy because it should be minus upper here and minus lower here, and it's written the contrary. So for example, if we apply the function to this value, the result breaks the invariant that the first member should be smaller than the second. So these type errors are tied to what we call constraint type. So constraint type attach a membership predicate to a type, and this membership predicate restricts the set of possible values the type can take. So such types can be constrained by numerical constraints, for example positive integers, or shape constraint, for example binary balanced trees, where not all trees are balanced. And also both, so when you have binary search trees that are balanced, they involve both numerical constraint and shape constraint. And the property we aim to prove, to verify at least, is that all of the function whose return type is constraint do not break the invariant. So in this work we will only focus on numerical constraint type, and to do so we will use automated random testing. So automated random testing consists in generating random inputs for programs or for a piece of program such as function, and test if the output satisfy the specification. So in our case, more precisely, what we will do is that for each function that manipulates a constraint type, we will automatically generate a set of input, apply the function to these inputs, and then check if the output satisfies the predicate. So if we go back to our example here, we provide an annotation to the type here, that is the pair of integers, and we annotate it to make it respect the following predicate. So this is to be read as the type interval is the pair of integers that satisfies the following property. And now, whenever we have a function here that manipulates interval, we add after the function the following tests. So here we first generate an interval, and then we check that applying applying the function to the interval does not break the invariant. So the hard part here is that the function generate interval should be derived automatically by our framework, and we want this function to be uniform. That is, every interval, every valid interval has an equal chance to being generated here, and we want it to be fast, because this will generally be embedded in a loop where we generate thousands and thousands of intervals and check if they satisfy the property. So to do that, we are going to talk about abstract interpretation a bit, in particular about the use of abstract domains in a constraint solving context. Then we will define formally what are the constraint types and how we generate generators for such types. Then we will talk about how we link the two, how we embed our constraint types within the constraint solving framework based on abstract domains. And then we will briefly discuss the different domains we use to do that, and we will talk about our implementation and the benchmarks. So abstract interpretation is a field of static analysis of programs in which the main idea is to prove properties by replacing expensive operations with less precise abstraction. And to do that, abstract interpretation provides well-suited representation for program states, which are called abstract domains. So here you can see a different example of abstract domain, which are boxes, octagons, and polyhedra. And intuitively, we can see that they are well-suited to represent a constrained space, where the constraints are linear, at least. And previous work has shown how to use such abstract domain within a constraint solver. So this is the work by Pello et al. And we reuse what have been done in this work. So I'm going to briefly recall it. So suppose we have a numerical CSP here, where we have two variables x and y, which are discrete variables. And their associated domains and constraint define the following solution set. So every blue dot here is a solution of the CSP. And solving such a CSP means to find all of these instances. So if now the CSP is continuous, so if both our variables are real valued, one solution can be to cover the solution space with some elements. So to build such a cover, we start from an initial element, then we filter it using the constraint. So we build a smaller element that contains the solution space. And then if this element satisfies the constraint, we stop. Or if it is smaller than a given threshold, we stop also in order to have our algorithm terminate. And if it's not the case, we split it in half and we continue with the sub-elements we obtain. So we'll filter them again, we check their size, and we split them again, and so on and so on. And by the end of the solving process, we have two kinds of elements, the blue ones, which are guaranteed to satisfy the constraint system, and the red ones, which are not guaranteed to satisfy it, but they were too small to be split again, so we have to terminate at some point. And this solving method works just as well with other abstract domains, sorry. So here in this example, we can see the solution using octagons. So what do we need to be able to use an abstract domain within this constraint solving method? We need a filtering function that reduces an element according to some constraint. We need a split operator that splits an element into two or more sub-elements. And we need a size metric to say when an element is too small to be split again. So now I'm going to present the type language we are interested in. So we consider a regular type language with atomic types such as integer, floats, and so on. We also have product types. So here tuples records. So here an example, a tuple where we have an integer and a float. We also have sum types. So sum types are somehow equivalent to enumerations in the C language. So here the type S can be either constructed using the constructor A, which takes an integer as a parameter, or the constructor B, which takes a floating point number as a parameter. And to this type language, we add constraint types. So constraint types are regular types to which we add a satisfying annotation which specifies which of these values should be kept. So our goal is to build for all of these types automatically a generator. So what is a generator? It's a function that takes nothing as input and returns a value of the type it is associated to. So if we want this to be uniform, every value of this type has an equal chance to be drawn. In the case of constraint type, a constraint type can be seen as a pair of composed with a regular type and a membership predicate. And its inhabitants are all of the values of the regular type that satisfy the membership predicate. So the generator should be constructed accordingly. So for each of our type construction, we have a rule that explains how to derive a generators for this type. So for example, for each composite type, we have a rule that explains how to derive a generator from the generators of its components. So if we take the example of the product types, so tuples in our case, if we have a tuple tau1 and tau-n, we build the generator that builds a tuple using all of the generators associated to the tau1s. So to tau1, the generator associated is G1, and so on and so on. And the hard part here is what to do with constraint type. So when we have a constraint type, we have to solve it to be able to derive a generator. So how to do that? So I'm going to explain how the solve function works. So if we go back to our introductory example here, from the declaration of the type, we extract a CSP. So the type interval, all of the inhabitants of the type can be considered as solution of this CSP. We have two variables with their domains being all of the possible machine integers values, and the solution are the ones that respect this relation. So we solve it using the solving technique I've shown before, which gives us this cover of the solution space. And now, using this cover, we are going to compile it to produce a code that will correspond to the generators. So to do that, we repeat the following steps until we terminate. That is, first we select an element of the cover. In order to be uniform, elements should be chosen with a probability that is proportional to their volume. Then we pick an instance that belongs to this element. Every instance should be picked uniformly. And then if the element was blue, then we have generated a value. But if it was a red element, so if it was an outer element, then we should reject values that do not satisfy the constraint. But if they do, we can keep them. And the termination of this procedure is probabilistic. That is, at some point, we will generate a value that belongs to the type. So the code corresponding to that is built as follows. So first, inner elements are compiled into generators. So this is the code that generates an instance for a blue element. Outer elements are compiled into what we call a rejection sampler. So this is something quite similar, but we use the reject keyword here to say generate a value using these generators, but keep only the ones that satisfy this predicate. And then we combine all of the generators for all the abstract element in the cover of the solution space into a list of generators, and we use the weighted procedure here that says choose one of the following generators according to the weight that are associated to each of these ones. So if we go back to here, this element, which is bigger than the other, will have the bigger weight and will be more likely to be chosen. So we have tested our framework with two different abstract domains that are boxes. You see here the resolution of the interval type using boxes, and polyhedra. So here, this is the solution of the interval type using the polyhedra abstract domain. And one interesting thing that we can see is that here we have 32 inner element and 32 outer element in this cover, which produces a code size of 500 lines and a sampling rate of 200,000 calls per second. So this means how many times per second can we call the generator. So if we compare this with the result we have with polyhedra, we can see that a single polyhedron is enough to solve, to cover the solution space. And the code size is much more smaller and the sampling rate is much faster. So I have not explained how to uniformly draw a point within a polyhedron, but it is explained in the paper, so you can take a look at that. So we have implemented this framework as a preprocessor for OCaml. So this means that when you compile your code to produce an executable, you can first give it to a preprocessor and then compile it, which will produce both the executable and the test. So using the same source code, so you don't have to modify the source code. All you need to do is to annotate the type using the annotation we provide. So this is available on GitHub if you want to take a look at the implementation. And we use as an implementation for abstract domains the apron library, and we also use the QCheck library that provides primitives for generators. So in order to benchmark the performances of our framework, we have used real types from some open source libraries, in which we have identified constraint types. So using our framework, we have annotated these types, and then we have benchmarked the generated code using different configurations. So using boxes, using polyhedra, by making vary the size of the cover, and also using rejection sampling. So these are the results we have. This gives some information about the constraint type, so the number of variables that are present in the CSP we extract from this constraint type, and this is the kind of variable constraint, that constrain the type. So BC stands for bound constraint and lint stands for linear constraints. So this is the sampling rate we obtain using rejection sampling, and by that I mean that no constraint solving is involved. Everything we do is generate value and keep the one that satisfies the constraint. And what we can see is that using constraint solving with these three different configurations, so that is boxes in the abstract domain with a cover size limited to 8 elements. Here the same thing, but with a cover size limited to 64 elements, and here with polyhedra. The samplers are much more faster. So in this example with boxes, we have a sampler that is 12 times faster than the one we have with rejection sampling. And when we have linear constraint, generally the generators we obtain with polyhedra will be faster, and sometimes much more faster. So this shows that using constraint solving to produce uniform generators can be really helpful. So in this work, we have seen how to derive automatically generators for constraint types. And as future work, we would like to extend our framework to make it handle functional values and recursive types, which are still a limitation for now. And that's it. Thank you for viewing. I would be glad to answer your questions.